Hello everyone, welcome to the fourth lecture of the Introduction to Deep Learning course here at TUM. Today we're going to talk about optimization and backpropagation, but before we will start with a new topic, I wanted to quickly recap of all the things we have gone over in the last few lectures. Especially in the last lecture, what we have introduced is this concept of a neural network. And we actually started with these linear score functions that we have known before, where we have a weight matrix W and we're multiplying to some input, and we're going to get a score F as a result, right? And if we are running the score function on something like a Cypher10 dataset where we have 10 classes, we're going to get these results that look something like this. So essentially, we're optimizing to get the maximum response from the score function based on the features that we're finding in X. And in this case, this is a linear model, meaning that W will simply encode stuff like what we see here, right? If you're looking at this example here we're seeing a car, and this is kind of the average car, which is like this reddish tone car, right? So for simple data sets, you can see these patterns, and these linear models can actually do something for image classification. However, it's going to get a bit more tricky when we have more complicated data sets. And if you do the same experiment on ImageNet, right, we're going to get results that look like these. So here we have many more classes, and we already see that, it's much harder to see some, known patterns. Sure, we see some distribution, but we don't really see the shape of a car or a horse or stuff like that. And the idea of the neural network was that we're starting with this linear score function, and we're just making it more powerful. And more powerful in this case means that we have a nesting of these linear functions, and we concatenate them with nonlinear functions, right? So in this case, if we have a two-layer neural network, we have here the input X, we multiply it with W1, that's one set of weights. We're taking this maximum function here, that's our nonlinearity, and we're multiplying it with W2, and then we get the score. And the idea of neural networks is that we can cascade these functions, right? So instead of having a two-layer network, we can have a three-layer network. Now we have two nonlinearities, we have three set of weights, we can have 4 layers, and so on, right? And in this lecture, we will very soon see we can scale this up very quickly, right? We can go up to potentially hundreds, potentially even thousands of layers that we can actually encode in a neural network. Now, typically, we abstract from that notation, and we often write this down as layers. So sometimes we see drawings like these ones that depict our architecture. So here we see our input layer, that's what X is in this case. We see our hidden layer, often denoted as H, and we see the respective output. In this case, it could be our score function. And what we also see is that every layer here has 3 neurons, this layer has 4 neurons and 2 neurons, right? And we see connections between these neurons, and these are our weights. And the number of connections we have here is equal to the number of weights. In this case, we have a fully connected network, means that, every neuron between 2 layers is connected with every other neuron of the next layer. And yeah, in this case, we have 3 layers, right? But of course, we can have a much bigger network. The only thing what we have to consider here in the structure, so everything is still structured into these layers. So we have an input layer, right? Hidden layer 1, hidden layer 2, hidden layer 3, an output layer. Then we have the network depth, which is the number of layers that we have here. And we have the width, which is how many neurons we have per layer. In practice, you often see stuff like this, where you have hidden layers with kind of a similar amount of neurons. Sometimes you don't have that. There's no guarantee. In principle, the width can vary per layer. But what is very important is we don't have any cycles here, right? So we have here input on the left-hand side, and we have output on the right-hand side, but there's no loop in the network. So all this goes from left to right. We also talked a little bit about what kind of nonlinearities we want to use. These nonlinearities in practice are called activation functions. We have seen this function here, we've seen now quite a bit, this maximum function. This is called the ReLU. We'll go into this in a bit more detail. We have seen the sigmoid function. This is often used for classification problems where you want to model it as a probability between 0 and 1, right? Because the sigmoid goes between 0 and 1, so we can interpret it as a probability. 10H is often used. That's between -1 and +1. Similar shape than sigmoid, a little bit steeper here. It flattens out a bit faster. Leaky ReLU is a thing, parametric ReLU, max out ELU, and so on. I should say there are some activation functions that do have learnable parameters. But for instance, the ReLU and the 10H and the sigmoid, they do not have any learnable parameters. The parametric ReLU, where we have an alpha here, would have a learnable parameters. But again, we will go into this a little bit later and what the implication is if we having learnable parameters in these activation functions. We have talked about the output layers, and the output layers is essentially being defined by a loss function then. So we have the score, right? And the score is being correlated with our labels. So what we have to do is we have to measure the goodness of the predictions of the network. We do this, of course, based on the training data. We can evaluate it also on the validation, but if you're talking about a loss function, we would think about during training, like how to optimize our training set, right? And that means we're taking the loss function into account in order to optimize for the network weights. We have seen a couple of losses so far. We have seen standard regression losses like L1 and L2 losses. We have seen classification losses, cross entropy we have seen, right? We have also seen we've seen the binary cross entropy, the special case, and here we have the generic case here with cross entropy. There will be a few more. We will talk about this a little bit more, but you can already see there's like these different types of loss functions for regression and for classification tasks. Okay, so the last thing we've talked about in the lecture were compute graphs. And these computational graphs is essentially an abstraction of the neural networks. And one of the reasons is why we can do that is because we can abstract the neural networks into these set of layers. So what is a compute graph, right? I mean, we have compute nodes. These are our neurons. We have edges that connect the nodes. And very importantly, these edges in this case are directional. So we always have this kind of flow from input to the output. And typically this is from left to right. And we can organize them in layers, right? That's what we do. We structure it. And later on, aside from the mathematical and abstraction here in the slides, of course, the layers also have some meaning when you're implementing neural networks. For instance, when you put it on a GPU, typically you run the network layer by layer. Good. So this is what we have done in the previous lectures. We know what a neural network is. We know how to evaluate a neural network. So we know how to do a forward pass if you have a given set of weights. We also know how to check how good the network works based on the loss function. And today we're going to continue and we're figuring out how do we actually find the weights, right? So we saw a little bit of simple examples where we did already some optimization based on gradients. And we want to continue that. And the big question right now is, based on these optimizations, we need gradients, right? And the gradients is a method called backpropagation. And backpropagation is one thing that we can do very, very efficiently with the way we write down these computational graphs. So in this class, all of the optimization schemes that we're going to use are going to be gradient based. I explicitly want to highlight that not all optimization schemes are gradient based. There's many, many other schemes. There's a lot of Monte Carlo methods, for instance, simulated annealing. These kind of methods, they don't do any, or genetic algorithms, they don't use gradients. They're very important methods, but we don't use them in the case of this class right now. I just wanted to be aware, not everything is gradient based. And who knows, maybe in a few years we will find that we can optimize the neural networks with different optimization methods. However, for now, for the time being, we're going to continue talking a little bit about gradients because that's what our default optimizations will be. And the tricky thing about neural networks is, we have many, many layers. It is very difficult to find an analytic gradient, right? In other words, it's very difficult to go ahead and, put on a whiteboard and figure out what are the partial derivatives with respect to potentially millions of weights in a neural network. And what you do in practice is we break down the gradient computation. And this is what backpropagation is essentially doing. Backpropagation is, instead of computing a gradient of an entirely big function, we are essentially breaking it down into a smaller series of chunks. And if we're looking again at our compute graph, again, this is a very simplified abstraction of our compute graph, same graph we had in the last lecture. We're having here input, x, y, and z. We're having a sum. We're having a multiplication. And this is our function f of x, y, and z is equal to x plus y times z. We have an initialization. This is just our input, right? 1, minus 3, and 4. What we do is we feed it in, right? So we're feeding in our input here. Our edges are forwarding this input. We have the summation here, that is -2 here as an intermediate result, and then we have -2 times 4 is -8. So this is what we have already seen. This is the forward pass. This is just taking the existing structure and the existing set of weights that we have, and the evaluating just based on the definition of the compute graph. Now the question is, when we want to do backpropagation, we're starting from the other end, right? We want to break down the flow of gradients. How is this result right now, depending on a certain loss, influencing whatever we're having here in terms of unknown parameters we want to optimize for? And the way we do backward is, first of all, we're looking at all of our compute nodes, right? In this case, we have this plus node here, and we have this multiplication node. So let's have a look at this plus node. We look at this d here. D is equal to x plus y. And what we do is, we do nothing else but applying the chain rule. And in order to do that, we're just considering every node independently. And what we want to do is, we want to figure out the partial of f, the entirety of the function, with respect to x, with respect to y, and with respect to z. And the way we're breaking it down, I mentioned it, we're kind of doing this chain rule idea. So for this node here, we're simply computing the partial derivative with respect to the two inputs, right? So here we have x as input and y as input. So we're computing partial of d with respect to partial of x, right? This is 1 because it's a summation, right? So this one here cancels out, and here we have a 1 left, and here it's the other way around. If we have the partial of d with respect to y, we're getting 1. For this product node here, this is this one, this is d times z. Well, if we are computing the partial f with respect to d, we have z. And if we're doing it the other way around, f with respect to z, we're obtaining d, right? This is standard algebra, standard analysis, very straightforward. But the nice thing is, this compute graph allows us to do this independently, essentially per node, right? So we can just take this node and this node alone. In this case, we had these two compute nodes. And now what we do is we're applying this backward pass starting from the right-hand side. So we're always starting here. In this case, we're starting with partial f with respect to partial f. So we always start here with a 1, right? And now what we're doing is we're considering this compute node. And what we would like to do is, we have here 1, right? And we want to compute here from this compute node the partial in this direction. So what is the gradient flow in that direction? And here we have partial f with respect to z, right? Z is the input here. And I can just look up here. Oh, f with respect to z is going to be d. D I know is -2, right? That one I know. And I just multiplied with this one here. This is kind of implicitly hidden. I'll get to this in a second. But I get here a -2, right? Because of this, because I'm just looking up this compute node, right? It's very straightforward because I have f with respect to z. Now, if I want to know the gradient in this direction, well, I do the same thing, except now here I'm looking up this one, right? And I have f with respect to d, and then I'm getting this 4 here. Again, I have this 1 here, I'm hiding this right now. At the end, it's very straightforward. I just have from the last output nodes, I just can take these results. Now, when I'm taking the summation here, I have to apply the chain rule, meaning that, oh, I want to know this sum. What is the gradient in this direction? Well, this is 1, right? So I have whatever we had here, this 4 times 1 is 4, so I get a gradient of 4 here. And if I do it in the other direction around, I have f with respect to x. F with respect to x is partial of f with respect to d times partial of d with respect to x, right? And it's straightforward because here we have, again, this is our f of d, this one is we have here, and d with respect to x, we have here, this is our 1, right? So because I have for every compute node, I listed out the partials here, I just have to look up respectively how to compute the chain rule. So I just need to know whatever is here times whatever this node is doing. It's very straightforward. This is the chain rule, right? This one here is always telling you what's on the right-hand side, what kind of comes in from the right. And this one here is what is the current compute node doing, right? So d with respect to x is here, and f with respect to d was here, right? So it's 4 times 1, and I'm gonna get a 4. Yeah, and then I have the partial derivatives right now of x with respect, so of f with respect to x is 4, of f with respect to y is also 4, and f with respect to z is -2, right? So I'm going to get the gradient with respect to all of these unknowns. Okay, yeah, let's have a look again at the notation. Right? We had here in our compute graph, we have here the input variables xk. We have our, again, this is a generic compute graph. Now I wanted to go back from compute graphs to neural networks. In our compute graphs here, we have the input variables xk. We have the network weights L, M, and N, the W's. Again, note the 3 indices. This one, L, tells you which layer, M tells you which neuron in a layer, and N tells you which weight in a neuron. Like this is like how many edges kind of are incident to a neuron. This is how many neurons I have in a layer, and this tells you which layer. yi hat, we already had this a couple of times, is the computed output. I is the output dimension, and we have a total of n output dimensions, right? Yi is the ground truth labels, and L is our loss function. So now I want to go into our neural networks, right? What we have seen before, we have an input layer and we have an output layer. That's our simplest neural network. Again, there's no stacking or whatever. This is a one layer neural network. What we have here, input x 0, input x1, we have our computed output, and this one we compare with respect to y0. Okay, and this is our class label, regression target, and so on. So we just compute a loss function here. Now, if you're writing this as a compute graph, this like one layer neural network, right? We can go ahead and have here x0 times w0. This is one weight. We have x1 times w1, right? We sum these two up. This is just our dot product, our linear model. Again, this is a one layer neural network in a sense because we don't have any nonlinearity here. We just have a linear model. We're summing these two up, right? And then we computing the difference, the L2 loss with respect to the ground truth. And now here I have a compute graph, right? So what I've been doing is now I transformed this like simplified neural network into a compute graph. And if we want to do optimization, what we are doing here now is we essentially want to compute the gradients with respect to all the weights, right? So in this case, I introduced a nonlinearity. By the way, this nonlinearity here makes absolutely no sense. I just introduced this for the sake of making it a bit more interesting. So now we have not just the linear model, we also have one nonlinearity. We have this ReLU here. This ReLU here, by the way, tells us, oh, we can only get positive output results. This is actually something you shouldn't do in practice. But I wanted to illustrate how we can take this compute graph and how we compute the gradients. So if we're saying, again, we have here the input, right? We have here the weights. These are the unknowns, so we want to compute partial derivatives with respect to W2 and W0 and W1. We have here this ReLU. Again, I'm not arguing this is the right choice here. And we have our loss function. And now we want to compute the gradients with respect to all of our weights W, right? So given training samples X and Y, these are our ground truth samples, we want to compute what are the respective partial derivatives with respect to W0 and W1. Now this is a very simple case. We can make this, of course, more complicated. Let's have a look at another case. Well, what do we have here? We have just 3 output dimensions here, right? In this case, we have x0 and x1 as input, 2-dimensional input. For each of these W heads, we compute, like we have 1 and 2 edges here, right? So we have x0 goes here, x1 goes here, and then you're adding this up. So this is one dot product, right? This is one dot product plus the loss function, right? This is the difference to the loss function. And see already we have here 2 indices. Again, we only have one layer, but we have actually right now we have 3 neurons. So we have the neuron 0, 1, and neuron 2. And for each neuron we have 0 and 1 weights for the respective edges that we have at input. We add them together and then get an as output, right? Okay, again, we want to compute the gradients with respect to all these W's, right? In this case, we have 1, 2, 3, 4, 5, 6 unknowns. This is what our neural network can optimize for. Okay, yeah, we haven't talked about the bias yet. In practice, we also have a bias. We have these activation functions. This is our very simplified neural one-layer neural network again. We have here this dot product of the inputs. we computing one yi hat, right? So we have 2 in this case. So we also would have 2 biases and so on. Activation, again, simplification, we just don't take a ReLU for the time being. Okay, so again, our goal is we want to compute the gradients of the loss function L. And the loss function is we just summing up all of these Li's. In this case, our Li is y hat I minus yi. Like we just taking the difference here to the ground truth, right, between these two. This is our L2 loss. And now what we're doing is we're summing all of these up. This is our total loss by summing up all of the output channel losses together. And now we use the backpropagation method. We use the chain rule in order to compute the partials. So which partials do we have to compute? Well, we have to optimize for these W's, right? Actually, we have to optimize for the B's too. But let's look at the W's first. Well, what do we have to do? Well, we're just looking again from the right-hand side. Here's our loss with respect to our yi's, right? This is whatever we are getting here. This is from our loss function. And then we're looking at this part here where we're taking whatever y hat was with respect to the w's, right? And this is very simple. We just go from right to left. We just have this gradient flow from right to left. And yeah, so we compute these gradients with respect to all the weights and all the biases. Okay, this is our very simple function. We can do backpropagation on that one. I wanted to show another example where we have these neural networks as a more complicated function. So again, if we're having our neural network here, we have here W1 times X, right? We're multiplying these two, we're summing these two up, we're adding the bias, and then we have our sigmoid. This is, for instance, a very simple computational graph we can have. Our function takes X as input, also the W's, and then we have here our linear part, and it's 1 over 1 plus e to the power of minus the linear part. This is just a sigmoid function here, right? We know this is our sigmoid. What we can do in practice, we could actually take this part away and could express this as one analytical part, but essentially we're expressing it as a full compute graph here. Yeah, and then we can do our standard backpropagation. And I wanted to show another example because the backpropagation is actually pretty relevant for many cases. Okay, let's have an example. Let's say we initialize our weights with W1, 2, W0 minus 3, our bias minus 3. X1 from the training sample is minus 1 and X0 is minus 2. Again, note, we're not optimizing for the x's here. X is just given by the training samples. What we really care about are the derivatives with respect to the w's and the b's. Well, what do we do if we want to do backpropagation? Well, we first run a forward pass. Okay, so we run a forward pass. 2 times minus 1 is minus 2. Minus 3 times minus 2 is 6. Well, minus 3 stays minus 3. We have minus 2 plus 6 is 4. Well, we adding it to the minus 3 here, it's 1. We're multiplying with minus 1, it's minus 1. We're taking the natural exponent. It's 0.37 roughly. This is rounded, this is not the exact number. We're adding 1, getting this one, and we're inverting it. We're getting 0.73. And if we want to do backpropagation, we do the very same thing what we've done before. We're taking literally every compute node that we have in this graph. Right? So we have the multiplications, and we have the exponent, the plus 1, inverse, minus 1. Okay, this is what we're doing here. I simplified this a little bit. So if I'm looking at this compute node, this is 1 over x. The derivative of function of 1 over x is minus 1 over x squared. Right? I mean, this is just standard differentiation. We have here this plus 1. This is constant plus x. There's only, if you derive with respect to x, we only get a 1. The derivative of this compute node is 1, so it doesn't change the gradient actually. E to the power of x, derivative is e to the power of x. And this compute node here is, this compute node here is constant times x, stays the constant alpha in this case, right? And yeah, so we do the same thing what we have done before, right? We start on a 1 here on the right-hand side, what we're feeding in from right to the left. And now what we want to do is we are applying again the chain rule. So we're taking 1 times the derivative of this node, and we're feeding in the respective input here, right? So it's 1 times, now we're looking up, 1 minus 1 over x squared, and we're feeding in the 1.37 what we computed the forward pass here, and we're multiplying with this 1. So the gradient here will be minus 0.53. Well, now we do the same thing for the next node, right? So this node here has a derivative of 1. So here we have 1, what we're getting from the node, times whatever we had here on the right-hand side. This doesn't change, that's what I mentioned. If you have a constant added, it doesn't change your gradient, which makes sense, right? But again, it's a chain rule. It's just simplified. We have again this times whatever the node is doing. Node is doing 1. This one was minus 0.53, which we still have here. Again, these numbers are rounded just for simplicity. Now we take the exponential function. We have here e to the power of x, e to the power of x. So what we have to do is we have to do e to the power of minus 1. This is this minus 1 that comes from the forward pass. Now we take the chain rule times whatever we had here, which is minus 0.53. If we're multiplying these two together, we're getting roughly minus 0.2, which is what we have here. Then we go to the next node. We have here, again, we have this constant alpha. So in this case, we have a minus 1 here. So alpha is minus 1 in this node. So we have minus 1 times the chain rule, again, what we have here is 0.2. So our gradient here will be 0.2. The plus node we've already seen, right? The plus node just forwards it. It's 0.2. Plus node 0.2. And here we have another multiplication, which is like this minus 0.2 times 2 gives you the gradient here, which is 0.4. And minus 0.2 times minus 1 gives you minus 0.2 here, right? I'm just taking the product rule basically here and applying the chain rule. Okay. Yeah, and here we have nothing else to do, right? We just have 0.2, the plus function just forwards again, so it's 0.2. Okay, so I would really advise you, if this was a little bit too fast, go back in the video, which is now a thing you can do in the virtual recordings, and really think it through how we go step by step from the right-hand side of this compute graph and applying the chain rule for every node and so on. And again, if you're doing this by hand, do what I have done here first. Like for every node, write down the derivatives. If you have to implement it, you actually do quite the same, except that you don't write them down, you just code them up, right? And then you can do the same thing what I've been doing here. Good, so the nice thing now, what we can do is we can compute gradients. Yeah, for simplicity, actually in practice, these x's, they shouldn't get any gradients. They don't matter, right? We don't optimize for the x's. We only optimize for the w's and for the b's. But of course you could if you wanted to. But in practice, you have a training set that is x and y given, right? And then you're optimizing for the w's and the b's. Good. Now we're taking the compute graphs, right? And we actually know now how to compute partial derivatives with respect to O weights, which is good. Now we can do gradient-based optimization. And this is exactly what we want to do now. We would like to talk, how do we do gradient-based optimization? And I'm sure most of you have heard how gradient descent works. It's not very complicated. What you're doing is, if you want to find the minimum of a function, so we have a function f of x. In our case, f will be a neural network later. And we want to find the optimal x that minimizes that function, right? And of course, if you have a two-dimensional function, I know that immediately that the optimum is here. But following gradient descent, if you, for instance, started here on the left-hand side, there's a local minima, for instance, here. Right? Be careful of local and global minima. That's another thing we will discuss a little bit. This is a local minima, this is a local minima, and this is a global minima. So in this case, what we want to do is we have this initialization. And for this point of f of x, we want to compute our gradient. So what we do is, we derive the function, right? So we compute the gradient. So we compute the gradient with respect to x of f of x. Again, our x will be our neural network weights later and our biases. And the gradient descent simply tells us, well, go into the direction of the greatest So, well, the gradient is the direction of the greatest increase of the function, and gradient descent means I'm going to descend, meaning I'm going in the negative, in the opposite direction of where the gradient is pointing. So gradient here points upwards, right? And what I would like to do is I would like to go downwards to find this minimum here. Okay, and the function is pretty straightforward. So what we have is we have an initialization x. These are my initial parameters of the function. I'm going to compute the gradient at this position f of x, right? It's the gradient with respect to x at f of x. I'm multiplying with alpha, and then I'm taking x minus alpha times the gradient, right? And then I'm getting an updated version here, which is ideally going down, and you iterate until you're down there. Okay, now we have this learning rate. This is essentially the step size that tells you how fast you should go down there. And we will talk a lot about the learning rate. This is a very complicated question, how to choose the learning rate, and there's many implications if learning rate is either too big or too small. And in fact, this is probably one of our most important hyperparameters when we're talking about optimizing neural networks. Okay, if you're talking about bigger neural networks, yeah, of course we have this big neural network. And in the following, again, I would like to highlight the notation here. So we have L layers, we have M neurons, right? And we're going to parameterize our weights with respect to L, M, and N. N will be the respective, like in this neuron, we will have N edges here that hit this neuron, right? Okay, so if we're doing gradient descent for neural networks, what we do now is we're taking a training pair, X and Y, and based on this training pair, we want to update all the weights, including the biases. I haven't written them down here, but they will come. So we want to update all the weights, meaning that we need to compute all the derivatives with respect to these weights. And that's what we're doing with backpropagation. That's what we've just learned. So what we're doing is we're taking f, x for a given training sample x and y, right? We're computing the gradient with respect to w, and we're getting this gradient vector here, which is f with respect to w000, w001, w000, and so on, until we reach w, l, m, and n. Again, check the notation, the indices here. L is the number of layers, m is the number of neurons, and n is how many weights are incident, or how many inputs we have incident to one neuron, right? So how many edges we have here tells us what this n here is, right? Oh, we also know how many weights we have. It's L times M times N. In this case, we're assuming we have the same M per layer. In practice, again, that might change, but if we had the same neurons per layer, this would be L times M times N. Okay, yeah, so we compute the gradient with backpropagation. We have just seen that. And then we can do a gradient step, right? So we do one step. So we take the current set of weights minus alpha times the gradient at this current step. And now you have already seen both ends, right? You have seen on one hand, I try to tell you all the variable weight algebra that is happening, and on the other hand, you already see this kind of like this high-level abstraction where I'm just going to write down a bunch of layers, right? And the reason why I'm going to do that is because these compute graphs, they become huge, right? They become hundreds of layers, if not thousands right now, with modern neural networks. And often you see visualizations that look like these. Same concept as before. Now, the problem is people at some point, they want to abstract away. They want to talk about high-level things, how to structure the layers and so on. Because the building blocks of each neuron is most of the time always the same. So that's why you often see visualizations like these ones. So this is this was a very famous paper from Google. This became this famous inception architecture. They already have like hundreds of layers basically, right? So you see you have kind of architecture diagrams that look like these. Yeah, so they can become quite complex, but don't fear. The nice thing is, if we're computing it, we're just going step by step through backpropagation and computing gradients, applying our chain rule, right? We're getting the gradients for each of the weights with respect. We're getting the gradients with respect to our weights, and then we can compute it for a given training sample. Okay, so if you're talking about the flow of gradients, we have many of these nodes from a neural network, and in practice, like state-of-the-art neural networks have millions of unknowns, right? So we have, again, I said we have maybe hundreds of layers, but we of course have many, many neurons per layer. So we have up to millions, hundreds of millions, sometimes billions of neurons. That is not encouraging you to also start with that, right? You should start very simple in your own neural networks, but I'll get to this later. So we have these neurons and we have a lot of these nodes. These are the neurons. And in practice, we're going to talk typically not about nodes. I'm going to tell you, well, we have neurons in our network and these neurons have weights and they're going to do something to the respective input and they're going to forward it. The nice thing, and I'm reiterating it here, is that each of these neurons has its own work to do. And the nice thing is about that is if you're implementing this, you can just have a function that represents a given neuron and you have this big compute graph and they just say, oh, use that neuron or use that neuron. And in practice, we're going to end up with a bunch of types of neurons that we're going to use. And these will define our layers. So we will have layer definitions. They have specific types of neurons. And then we have different architectures. They are a collection of these layers, right? So for each neuron, what we have to do, we have to compute the forward and the backward pass. And the nice thing about the flow of gradients is that we can consider each of these neurons actually independently. So if we're having a function here, f, right, we're getting x and y here as input, we're computing f, x of y as z. Like literally locally, we can compute our gradient. So we have here activation, f is our activation function in this case. We're getting here our gradient from the right-hand side as input. We don't know what's going on there on the very right, but we do know through our backward pass what is our gradient flow from the right. And then with respect to the two inputs here, we're computing the partials with respect to f, right? So we have z is our output of the neuron, and we're computing the partial with respect to x and the partial with respect to y. And all we have to do is we only have to apply the chain rule, which is whatever we have on the right-hand side times what the neuron does with respect to the given input, right? And this is pretty nice. It's actually very simple because you can easily implement this by having a for loop, go over every neuron, compute the partials, and multiply it with the gradients, what you're getting in the output. So it's actually straightforward. And yeah, of course, this is something that people have figured out in the 80s when they introduced backpropagation. But this is mathematically, it's very, very old. In fact, we know through differentiable algebra, right, that the chain rule is very straightforward to do, and we can use it to break it up more complicated functions, right? So this is something that we know already since Leibniz and Newton, that we can compute the respective partial derivatives using the chain rule. Okay, if we do now gradient descent for neural networks, I wanted to show you again a very simple example. We have here neural networks with our input layer, hidden layer, output layer. We have here x0, 1, 2, 3 as input, so we have 3 input dimensions. We have 4 hidden neurons, and we have 2 output neurons. So we have 2 output dimensions. We have a loss function. Our loss function is just whatever we're predicting as scores minus our ground truth squared. So we have an L2 loss. We do have the score function being defined. Our score function is defined based on the linear part of these neurons here, of these two. So we're taking 1, 2, 3, 4, 5, 6, 7, 8 inputs into the 2 neurons, so 4 each respectively, right? We have our biases here. These 2 have biases. We have an activation, and we're just going to use a ReLU for now. It's our maximum function. Again, I want to quickly, I always like going over the indices. I think this is very important. So if you're checking here, this W1 here, the first index here is 1. Why? It's the second layer basically, right? Here we would have 0, which is corresponding to this layer, and here we have 1, which is corresponding to that layer. So these are these weights denoting these edges here. How many of them do we have? Well, we have I and J, right? So we're going to have this J is going to go over for one neuron basically, right? I is which neuron, and J is the nodes in the neuron. So this J will be 4 because this neuron will receive 1, 2, 3, 4 input edges. So this J goes over 4. The I is how many neurons do we have? We have 2. So I could be either 0 or 1, which is corresponding to Y hat 0 and Y hat 1. For B, for the biases, we mentioned it, we have one bias per neuron, right? And then we have the activation function, which is, there's no parameter, it's just the max function. And this is how we compute the yi heads, right? I, we have 2, J, we have 4, and W1, because we are in the next one. Well, and of course, this J here is determined by how many H we have here, right? Like this tells you how many edges you have to have. Okay, we do the same thing here for this layer. Now we have to count these edges. Now our W0, because it's the 0th set of weights, we iterate here over K, because K is the respective input we're getting here. K is 3, because we have 3 neurons in the previous layer. That's very straightforward. We have J, that's the number of neurons here. 1, 2, 3, 4. Right? And so we have 4 biases, and we have 4 J's here for the weights, and we have 3 K's for the 3 respective inputs. We have another activation. Again, we're using just the ReLU in order to compute these. Now we can also compute how many unknowns do we have. Well, it's straightforward. It's 2 times 4. These are 8 weights, plus 2 biases is 10, right? This would have 10. We can do the same thing here. So here we have 4 times 3 would be 12, plus the 4 biases here would be 16. So we have 16 plus 10 number of weights. And yeah, you can go ahead and count it too. So hopefully I did do this right. And of course, you can imagine if you're appending more layers, you will of course have many, many more unknowns. Good. So now we're just writing this one down, right? So we have our forward pass here, which is defined by how we compute the H, the hidden layer. We have, based on the hidden layer, we know how to compute the respective outputs and the predictions by I hat. And we have our loss function that we can compute based on the outputs with respect to the ground truth. Now, backpropagation means, again, applying the chain rule. What do we want to derive for? Well, we want to get the weights here, and we want to get the weights here, including the biases. So we're going to go with respect to our loss function. We want to have these set of weights here, so the W1ij, right? In order to get these ones, well, we want to figure out the loss function with respect to our yi hat. Well, this is what we're doing here, right? And the loss function, by the way, is defined here, right? So we're taking the loss function, we're deriving this one with respect to yi hat. And then we're taking the node computation of the linear part, which is yi hat, with respect to these w's here, right? So this one is the derivative of our loss function, of our L2 loss, what we're getting here, right? Well, and here we just take wi hat with respect to our w's. This is what we had here from the input here, right? Because this is just our multiplication. If you're looking here, we're just taking this function here and we're deriving it with respect to the w's. So this one here cancels out the biases. And of course, we just remains, these h's will remain. This is what we have here. This is hj, right? Of course, there's only if this is greater than 0, otherwise this is 0, because we have the activation function here, right? So now we we get the chain rule, we can just derive the compute nodes here. We have this compute node, we have that compute node. We just formulated it out, we computed the derivative. And all we're doing right now is we're just going through layer by layer. If we want to compute now loss function with respect to W0, these are these weights here. Well, I'm just going to go ahead and in addition to what we've just done, we first compute the derivative with respect to the loss. That's what we have here. By the way, this one we already computed. So we can cache it. That's what the gradient flow is doing. And now we're taking wi hat with respect to hj. We can do this here, right? We're going to get the gradients will be our weights here, by the way. Just to clarify, right? If you're deriving this function with respect to h, you're going to get the weights here. And then you're multiplying it with hj derived by the respective w. So we're taking this function here, and here we will get x as a result. So I haven't written it down now, right? But it's very clear. This part here is our loss function we've already derived here. This part here will be these weights here. And this part here will be these x's here, right? These are the respective derivatives. And the nice thing is, because it's a chain rule, we just multiply it all together. And if we had another layer, we would just append another term here. It's very straightforward. Okay, very good. Very good. Now we know how to do like this is basically now the compute graphs on the neural networks, right? So it's what we've learned on the compute graph. Now we can directly apply to a practical example with our very simplified neural network that has one hidden layer, and we can compute the partial derivatives. I did this already, like how many unknowns do we have? Well, we have here 2 times 4, right? 2 times 4 plus the biases here. So neurons times input channel times biases. Hidden layer has 4 times 3, 4 times 3 plus the 4 biases of this one, right? This one is 10, this one is 16. So we just sum these two up, right? Okay, I mentioned this already before. Some activations do have weights, but in practice for now, we're not going to have them. So I'm just going to ignore it, and we will have only neurons and input channels that we have to consider, plus their respective biases. Very good. Okay, here's another example on the slides. I'm not going to go into that. I don't want to make the lecture video too long. This is something we will go into detail in the exercise sessions, but you can also do this as a homework. You can go ahead and do the same thing what I have been doing for the L2 loss. We can take the same neural network and have a binary cross entropy loss. So in this case, our score functions will be based on the sigmoids. Our scores will be still linear. But in practice, you would do the very same thing. You would apply the chain rule. You would get these concatenation of these terms. The only thing you have to do now is you have to compute the partial derivative of L with respect to y, which is, you know, this term. You have to derive that one. You're going to get this here as a result. And this one here is this y here. You're going to derive it with respect to s. You're going to get this here as a result. Yeah, this one is easy again. You're going to take the score function. You're going to derive it with respect to the weights. That's h. But please do this at home. Have a look. Make sure that the algebra here is actually right. You always make mistakes. Just make sure that you understand how to do derivatives again. I just want to keep it a little bit shorter here. I don't want to go into too much more detail because I still have a few things I would like to cover in this video, and I don't want to go into too extensive detail. And at the same time, I would like you to have a bit of a practical exercise on your own going through it. In principle, you can do this with any function, not just for binary cross entropy. It's always the same thing, right? You just have to know for every node, these are our nodes here. This is our loss node, so to say. This is our output node, and this is our score of the neurons independently, right? And we just have to go ahead and compute the partials, and then in order to get the weights, we just multiply them all together. Good. Yeah, I'm going to skip these ones right now. Again, this is something you can do at home, and you can see what kind of derivatives we're getting. Good. Very good. So I would like to go back now to the compute graphs and the neural networks, right? We've talked about this now quite a little bit, right? We have here, this is our nice compute graph of our simplified function. We have here our x is our input, our w times our z. Z is our intermediate output, right? We feed this z into our activation function sigmoid O max. Then we have another W2, right? We're feeding this one here in, getting the scores, computing the scores with respect to the loss, right? And now what we want to do is we want to optimize that function, right? We want to optimize with respect, with respect to what? With respect to the weights, of course, right? With respect to the weights and biases. Again, biases are omitted here, and that's what we want to do. Okay, here we have this optimization very quickly visualized. So now we initialize, we have our training sample, x and y given, it's 1 and 0. We have our weights given, weights is 1 and 2, so it's 1/3 and 2. Our loss function is defined by an L2 loss, that's what we have here. N and D is our respective dimensionality, it's 1, just to make it a little bit easier. And then if you're looking at the loss here, we can just compute the derivative of the loss function, right? So this is 2 times y hat minus x, it's just standard derivative. And then we're computing the derivative of y hat. This is w times the sigmoid. And yeah, this is basically the sigmoid remains here, so we need the derivative of the sigmoid here. Okay, so if we're feeding 1 here as input, we are doing the forward pass, right? Okay, we can go back quickly. 1 times minus 1/3, we're getting 1/3. 1/3 here times 2. 2 times 1/3 is going to be 2/3, and y was 0, so we're getting 4/9 as a loss. Back propagation means here, again, we're starting with a 1 here. Then we're getting 1 times what we have computed from the loss node here. It's the 2/3 times 2 here, right? Because we have this 2 here. This one was 0. This one we had 0, and this one here we had 1, right? So we have 2 times 2/3, which is 4/3. Then again, if we could continue, then we have 2 times 2/3 times 1/3. So we now just continue going through here, looking at this node here, and so on. And we're doing this back propagation throughout the entirety of the graph. Again, I went through this a little bit faster right now. This is something I would recommend. Have a look at home and check if everything's correct. This is very, very, very important. But again, the thing what to do here is you always have to look at the nodes. In this case, right, we're looking at this node here for the loss, right? 2 times 2/3, and then we're getting the 8/3 here. Then we're looking at this max function here, right? Again, could be also sigmoid or whatever. This is maybe a bit confusing. Like this is not the sigmoid function here, but it could be. And then we're deriving this with respect to z, and so on, right? And then we always have whatever this node gives as its own derivative times what we have on the right-hand side. In this case, this was a 1, right? In this case, this was a 1. In this case, this was also 1, and so on. Okay. Yeah, and at the end of the day, we're going to get for this W1, we're going to get a partial derivative, and for this W2, we're going to get a partial derivative. Now, in this case, I've already done it right, meaning that I didn't compute a partial derivative for x and for y, because these are our respective training samples. Okay, so we compute the gradients with respect to W1 and W2, and we're going to get a 2-dimensional gradient here, because we have 2 weights. Again, this is very simplified, and I'm ignoring the biases and so on right now, but I'm making this a little bit easier. And now what we have to do is we have the partial derivative for this given training sample with respect to W1 and W2. And now what we do is we update the weights, and this is just a gradient step. So what we do, we're taking our original, so we're taking the gradient descent formulas, saying the original weights minus alpha times the gradient which we just computed. The original weights were W1 and W2. The gradients we just computed were these ones, basically 4/9 and 8/3 that we can put in here, right? So we have 1/3 and 2 as the initial weights, alpha times whatever we have here. Yeah, the tricky thing which still remains is how to choose a good alpha. And this is something, what I mentioned, this will be something we have to discuss a couple of times throughout the rest of the lecture. Okay, so I hope this was an example that illustrated how to do backpropagation first to get gradients through our compute graph. And in this case, the compute graph was already formulated as a null network, so we had our loss functions, our linear layers, and our nonlinearity. And once we had the gradients, we can do our gradient update. And we can do one iteration here in this optimization process, and then we get a new set of weights. Now, in gradient descent, I mentioned it already, the learning rate is a very, very complicated thing, and we haven't talked too much about it. How do we pick a good learning rate and so on? That is actually very, very tricky. This is a very, very tricky hyperparameter. There's a few other things, actually. How to compute a gradient for a single training pair. This is an interesting question because that's actually always what we have done so far. In all of our cases, we have always taken one training sample, and for this one training sample, we have computed now the partial derivatives. So if I'm quickly going back here, right? In this case, we have taken the training sample x and y, and we have computed the partial derivatives with respect to this one training sample. And of course, you can already guess, right? If I'm taking an image classifier or so, x is like a high-dimensional image. We have, I don't know, like a few million weights in our network, and our class label is just one label. You will see that getting good gradients from a single sample might be a bit of a problem, so we have to think about possibly how we have then multiple training samples incorporated in this process, right? And this is a big question that we have to talk about soon, like how to take many samples and incorporate them. And I can already give you a little bit of a spoiler. What we're doing at the end of the day, we're taking multiple training samples and then averaging the gradient over these multiple training samples. If we're doing full gradient descent, we would actually take the entirety of the training set and computing one gradient for the entirety of the training set, right? And this is basically the average of all the gradients with respect to one sample. So if you're running a neural network, you could in theory go ahead and compute the gradients with respect to every training sample independently, and you can just compute the average between all of these. Yeah, you can already guess this might become very slow when we have big training sets. Like ImageNet we mentioned has like 10 million plus images. So in that case, we have to think about how we speed this up. And I can already give you a little bit of a spoiler here. We can compute approximate gradients, so we can estimate the gradients by only taking a subset of the training set. This is something we will later call stochastic gradient descent. So we're only taking a random subset of the training set in order to compute these gradients. But the core method here is always going to be the same. And again, remember that. What we're doing is we're taking a training sample. For this one training sample, we're computing a gradient, using backpropagation to do that. Once we have a gradient with respect to all the unknowns in the network, which is the W's and the B's, weights and biases, then we have our gradient with respect to these, and then we're doing a gradient update step. And again, we have to check out learning rate and stuff like this. But that's the high-level algorithm. And what we're doing is we're running this many times, right? We're doing many gradient update steps, and hopefully at the end of the day, our gradient descent method will converge and give us good network weights for that given training set. And if we're going one level higher again, once we have optimized and we have trained our network, then we can take these given weights at test time and apply them for evaluation. So we can use them to make predictions on data that was not part of the training set, and we can do learning. Again, everything we're doing right now, by the way, there's the learning part means we're just looking at the training set, and we're hoping later on that what we're optimizing here will also apply to a new data distribution. Okay, and with that actually, I wanted to talk a little bit about this generalization problem, right? So one problem what might occur is if we're doing this gradient descent optimization, that we're just literally memorizing our training set, right? And we would be very good at our training set to do something, but we would be not very good at evaluating unseen samples. And this might be a problem. And this is one thing which we typically deal with in the regularization. And I wanted to discuss that concept quickly because this goes kind of hand in hand in how we do optimization. Again, we're going to talk about the different optimizers in the next lecture, or different variations of gradient descent we're going to talk about in the next lecture. But now I wanted to talk a little bit about the regularization concepts. And remember when we're talking about the basic concept in machine learning, right? What I said is, I think in the first or second lecture, we had these splits of our data. We have our training set, we have a validation set, and our test set, right? We have 60-20-20 splits or 8-10-10-10 splits, right? But the big thing, what we have just discussed in optimization, is we're only taking the training set here. Based on this training set, we will compute our gradients with backpropagation, and we will do gradient descent in order to find network weights W and biases B. This is what we will do only on these 60% of the data. The validation set we will then use to figure out, well, how does it work on samples that were not directly part of this optimization? That's validating it. And we will make certain changes, like changing the learning rate, for instance, based on the validation set and stuff like that, right? These changes we will make based on the validation set. And then at the very end, we do testing. Again, testing we do only at the very end. But what I would like to talk a little bit more about is the problem is basically, what is the generalizability between these two then, right? Like if you're training here on a certain samples, do this gradient-based optimization, how well does our network perform later on validation and test? That is a big question. And there's these concepts of over and underfitting, right? So here we have an example where we have a bunch of samples. We have these crosses here, and we have the circles. And we're having a single line here where we want to divide, we want to have a decision boundary that divides and splits these two classes. Now we can very quickly see it is not possible to move this line in a way such that it perfectly separates the two out, right? Like I can't fit it in. Like some of the blue circles are here and here, right? And some of the red ones are intersecting in the blue territory. So because we have this kind of non-linear distribution of our data, like a linear decision boundary is not good enough. So this is underfitted. This means if I'm just looking at the training data here, I'm not capable, my model is not big enough or has not enough capacity in order to properly explain the training set, right? It can't do that. And this is something what we should call underfitting. So underfitting means training loss cannot go down enough, basically, right? We have this problem. We have the other extreme case, which is the overfitting case, which is that one here. In the overfitting case, we perfectly fit a line. Let's say we have a model that is very, very big, right? It has a lot of capacity, and it just will perfectly fit this line here to the training set. But the challenge with overfitting might be that it doesn't maybe generalize too well. So it does it perfectly on this one here, but it doesn't, it doesn't do it very well in generalized case. And a very good example for image classification is if I'm just memorizing image colors. So if my color in the middle of the image is red, it's a car. This works for a certain sample in the training set, but it doesn't work very well in the generalized case. They need better features, right? And this is what the appropriate solution should be. It's like somewhere in between, right? I'm having a combination between the underfitted and the overfitted case. So I want to have not just the linear version that is not capable enough to splitting it well enough, but I want to have a good enough split at training, which I hope will later on generalize. And this is the whole idea of machine learning, right? We have this training set. We're hoping to explain this training set well enough, but not too well, right? Not too well. Such that we can still do generalization later on. And this is these three things here are very important for you to memorize when we're looking at doing the optimization now for the neural networks. And if you're looking specifically at our training validation curves, we can pretty quickly decide in which case we're in, right? So if this one is our model capacity here, right? And this one is here our error, basically what's happening, well, at the beginning, of course, if you have zero capacity, we cannot explain our training set, right? If we are making our model bigger, our training error will go down, and our training error will eventually go down to zero. If I have a model with infinite capacity, my training error will be zero, assuming optimizer is doing okay in this like infinite dimension. But if I'm okay in this infinite dimension, right, my optimizer should be able to memorize my training set. So this is great because I will get a training error of zero. The bad thing is it has zero generalizability because I simply memorized a bunch of examples, right? And basically what we're looking for is this kind of optimal capacity, right? We're trying to figure out, oh, yeah, we're not memorizing all the training sets or the training samples, but we still do it such that we learn good features, which makes the training a bit harder. So we don't just memorize, but we're learning rather patterns that we can later use these patterns in order to get also some results on the validation set, right? And this is the green curve here, right? And we can quickly, if you're drawing this curve with respect to capacity and error here, we see at some point the green curve has an optimal value, right? The optimal value of the optimal capacity. And yeah, in this case, if we're in this realm here, the training error is too high. And in this case here, the generalization gap is too big. This, by the way, is the generalization gap, meaning how well do we generalize between the validation and the training set. Now, ideally, what I would like to do, I would like to use a big model to learn better features. But if my model is too big, I will have a bigger generalization gap because my model will just generalize stuff. I will just memorize stuff. And the big question is, how do we prevent this model from overfitting? This is a very common problem in machine learning, that we always end up on this side here because we tend to have too big models. We need big models, right? But we don't want to just memorize stuff, but we want to generalize. And this is a thing where regularization comes into play. So regularization means, on a very high level, I want to make the training harder. I want to have a big model possibly, but I want to make the training harder such that it is less likely to just memorize specific samples, right? And what this means in practice is we're just taking our loss function, like we had this L2 loss function, and what we're doing is we're adding a second loss here that we want to optimize, as a so-called regularization loss. And this loss could be multiple things like L1, L2 regularization, and we're adding this loss here to our L2 loss. We're scaling it with lambda here. This is our regularization weight. And this is dependent on the network parameters. So if we're having an L1, L2 loss, it would mean that, oh yeah, like just add a second loss to like high regularization, high network parameters. These are the two I wanted to talk a little bit about right now, about L1 and L2. There's other ones like max norm, dropout, early stopping, stuff like this. We will talk about this one later. But first I wanted to introduce this concept of regularization and what the effect it has on the parameters based on L1 and L2 regularization. Okay. So if you're looking at a simple regularization example, let's say I have an input which has three-dimensional feature vector, 1, 2, 1, right? Very simple three-dimensional feature vector. What we want to do is we have two linear classifiers here with two different weights, right? We have theta 1 and theta 2. And these ones are just literally multiplying. This is a linear one, right? So this one is just 0 times 1, 0.75 times 2, 0 times 1, and so on. And here it's 0.25, 0.5, and 0.25. This is just a linear model here right now. I just wanted to make this model very, very simple. And I wanted to quickly talk about the implication about these two choices here. If we are having this choice here, that would mean if my model has zeros in weights with respect to the inputs, it would mean it literally ignores these ones here and it just has 2 times 0.75. It means 2 of the input features are being ignored, right? So that is it's not necessarily a wanted desire, because it might be something like, I could just memorize this 2 here. That's easy. But if I do that, this is enough already to get my training loss to 0, so I don't need these other 2 features. And this is a result possibly of a training. The second one takes the information from all of them, right? Now it has a linear combination between these two. It gives you the same score, but it does use all of the input features. So the assumption is that if you're using all of the features at the same time and distribute these ones, this second set of weights has more potential to channelize. And that's very important for us, right? Okay, so let's have a look at a practical example here with regularization now. And this is how we can enforce which one of these two is better or worse. And we wanted to use a regularization term that is L2 regularization based. Later on this will become weight decay. We'll talk about this later, but I just wanted to keep the concept simple. Here we have theta squared, which is saying I'm going to penalize very big weights in a squared sense. Right? If I have big weights, they will be penalized quite heavily. So I want to have rather small weights, and of course you all know it. If you're having an L2 regularization or an L2 optimization, the optimum of an L2 optimization is always going to be a mean. This one will mean it will spread out the weights as much as it can. If I'm looking at the sparse sample weights, what we had before, the 0, 0.75, and 0, this one will be 0.56, right? The second sample will be much lower because you have this 0.5 squared versus the 0.75. These are square terms, and the square terms makes the bigger numbers being penalized more because it grows quadratically, right? So the second set of weights here is lower in the loss, only the regularization loss right now, than the first set of weights, right? So again, this input, this set of weights and this set of weights, our regularization here would say this one would prefer it. It would prefer this one here because it distributes it more. It doesn't like big outlier weights like these ones. So this would tend to memorize stuff. And this is not what we want, right? Okay, and yeah, so we have this minimization now that we jointly optimize for all of these. And with the L2 regularization, we would rather end up with that one. I mean, this is just a made-up example, but this is an example where we can see an L2 loss will favor this example here, right? Okay, if you're taking an L1 loss, like again what we're doing right now, if we're going here quickly, now we're taking L1 regularization. L1 regularization would say, well, we're just summing them up. It's 0.75 here, and it's 1 here. So L1 would tell us, favor this example here. Right? It has a smaller weight sum than this one. Right? This one is 0.75. So this one is 1, and this one is 0.75. Now, what does it mean? Well, it means the L1 loss would actually favor this example here. I can already give you the spoiler. L1 regularization for weights is not necessarily a good idea, because L1 regularization does tell you sparsity. And that is a very important concept that we have to see. Again, if you're taking this example here, L1 would enforce sparsity. That tells you, well, concentrate more on one, and L2 would tell here enforce that weights have similar values. And it's very similar if you've done optimization. The optimum of an L1 optimization problem is the median, right? The median here is, this is the median here. And L2 optimization would say it's the mean, so it would equally distribute, right? Okay, but I wanted to quickly tell you what this regularization means if you're optimizing for that for a classification. So if we're having a classification result, sparse versus dense, if you're taking an L1 regularization, all of the input features here have different meanings. If you take an L1 regularizer, it will focus only on key features. It will focus only on like has two eyes and has tail. Of course, this is one example, but importantly here is that the sparsity will not consider all the other information it has. And I think that's a very bad thing, and it will lead probably to more overfitting what we have seen before. Right? If you're doing L2 regularization, we will distribute the weights and we will consider all of them. We will force the network, even though it doesn't know right at the beginning that it needs all of this information, but we think it should focus on all of them. So it takes all information into account to make it kind of a more informed decision, right? It's not making a greedy choice. It's like, oh yeah, if tail equal dog. No, it takes all of the things into account. And it's considered more robust, and we will see this is much better property in terms of generalization, because we don't just memorize individual features, but we force the network to take everything into account. Yeah, if you're writing this regularization down as a compute graph, we will get something like this, right? So here we had our original neural network here. And now the only thing what we have is we have this regularization term, right? We're taking this W1 and W2 here. We're feeding it here in our regularization term, L1 or L2 loss, whatever we want to use. Well, typically L2. Times lambda, then we're adding it here up, right? And we have a combined loss between the two. So our combined loss is the original loss from the loss function of the network, plus the regularization term W1, W2, right? Okay, that's regularization. We can also make this practical, right? If we have an L2 regularization, we have here W1, W2, and we have the L2 norm of this whole thing. That's what our regularization is doing for us. Good. Oh yeah, I can also write it down in a more simplified way. We have W1 squared plus W2 squared. Good. If you're looking at the decision boundaries, what regularization has, right? I mean, of course, there's this lambda parameter here that we can play around with. If you're looking at that one, we have here different decision boundaries, right? We have a two-way classification problem here. If we have no regularization, we might end up with this kind of stuff, right? That we have like these noisy decision boundaries. But if you're making the regularization term stronger, you will get more smoother boundaries, right? So the regularization right now gives us the opportunity to say, oh, we want to have a more fine-grained decision boundary, or we want to have a smoother decision boundary. So it's kind of the smoothing term that we can add that tells us how smooth is our decision boundary. And yeah, what's the implication of that, right? The implication is if I'm making the regularization term too strong, let's say I'm setting this to infinity, I will basically, if I'm going back here, I will only optimize for that term and not for this term. So I will just over smooth our results, make sure all the weights are the same, but then I'm not learning anything anymore. That's also a problem, right? So if the regularization term is too strong, that's also an issue. So it's tricky, right? We have to find the right balance. If regularization is too weak, then we're going to overfit because we're just memorizing specific features, right? So we have to find a good balance of this regularization term. And I would argue that yeah, the regularization hyperparameter is basically in addition to the learning rate. These are two very important hyperparameters. So now we've already heard about learning rate, and we've talked a little bit about regularization. We will very quickly see, regularization is important as a hyperparameter. And we have this balance, right? If too big, then we don't consider the first term anymore, we don't learn. If too small, then we probably overfit. In practice, regularization, you can see it on the training curves and the validation curves. If your validation curve and the training curve are roughly the same, but they don't go down all the way, then your regularization is probably too big. If your training curve goes down very quickly and your validation curve doesn't go down that quickly and there's a gap in between, then you should probably add more regularization. That's kind of the rule of thumb. That's why it is so critical to look at your regularization, at your training and validation curves in order to figure out these design choices, how to set your parameters here. Good. If you're talking about a little bit higher level again, what's the goal of regularization? I mean, I told you a little bit of the implications right now, right? When you make it bigger and smaller. In a sense, if you're thinking about this concept of machine learning, right? What we said is, we're trying to train on a training set and then we're hoping that this generalizes to unseen examples. In a sense, what regularization does for us, it wants to actually make the training harder. And this is something when I'm advising like student thesis and stuff like that, I'm typically asking them, why do you regularization? And said, you want to make the training easier. No, you want to make the training actually harder so the network has to learn better features, more powerful features that are potential to generalize. So training harder means typically you have more generalizability. Of course, the training is too hard, then you aren't learning anything anymore. That's also a problem. But that's why I'm saying you have to have a good fine-grained implication. Yeah, what happens to the training error? Well, of course, if you're adding a second term, it will make the training error higher. But I just wanted to clarify, if I'm going at this formula here, and I'm increasing this lambda weight here, so the network has to focus more capacity on fulfilling the conditions of this regularization, it will inevitably make this error here higher because the network cannot focus solely on this part. So if I'm optimizing for two terms here at the same time with a reasonably high lambda, it will have a higher loss here than if I didn't have the lambda, right? So in other words, my training error will go up if I add regularization. Not just because I'm adding the second term because of the second term's sake, but also because I have to focus on something else and not only on one term, right? So training error will go up, but the hope is that the validation error will go down. So that's what we're aiming for. We will aim for low validation error and increasing the training error. I can already tell you if your training error is too much increased, then your validation error will also go up. But the regularization has this nice property. You can balance training and validation errors against each other, right? Basically, this lambda parameter tells you if I set lambda to infinity, my training will not go down at all. If I'm making lambda smaller and smaller, my training error should go down, well, depending on how much capacity I have in my model, of course, but it will go down more. But in principle, my validation error could go up, right? So there's a fine-grained sweet spot how to set the two. And this is something I would really advise you, like, play around with it. This is like, this is what AI eventually becomes to, right? AI is a thing where you have a function, you want to optimize it, you want to find some features, and you're hoping that these features generalize to new scenarios, and you can generalize. And regularization is kind of this key concept that you have to do during an optimization, right? I mean, we talked about the optimization now for quite a while with gradient-based optimization, with backpropagation and so on. We'll go into more details there. But my point is, in this optimization, you don't just want to memorize whatever's in your training set. You hope to find features that do actually generalize to new samples. And that's the important thing we will continue talking about. Okay, I'm actually mostly through the content. I mean, this week, obviously, we have the exercises, right? Check those. We have the office hours. They're still virtual office hours because we still have a COVID-19 situation going on. So make sure you take advantage of all the offerings that we have. We want to make sure that you're all being covered and you get all the support you need during this lecture and this course. If there's anything unclear, post your questions, right? Like, ask questions. That's very important. Post them in Moodle, ask the TAs, and so on, right? Very, very important. In the next lecture, we will continue with what we've started today, right? We have already talked about gradient-based optimization. In the next lecture, we're going to talk about what I already hinted a little bit. We were going to talk about what variations of gradient descent can we use. Do we need to use the whole data set or only one sample in order to compute a single gradient update, right? How do we do that? In particular, we will talk about SGD, this stochastic gradient descent method that is kind of this compromise. We kind of trying to find a distribution of training samples that estimates a good gradient. That's what we're going to talk in the next lecture. And in fact, there's a lot of variations of that, and these all make a really, really big impact on how to optimize and how fast we optimize it. So with that, yeah, again, I would like to thank you for watching our video. Yeah, otherwise, of course, stay safe, stay healthy, and enjoy hopefully the videos that we're recording here. Okay, there's a bit of further reading also in terms of backpropagation, which we appended at the end of the slide deck here. Yeah, please have a look. Yeah, otherwise, see you next week. Stay safe, stay healthy.